This lesson is about a change in mindset. Up to now, code may have felt like a sequence of instructions that run from top to bottom. Functions introduce structure. They let you isolate behavior, give it meaning, and reuse it without copying and pasting logic all over your program.
And this idea of reuse has very practical consequences. When the same operation appears in multiple places, changing it becomes risky and error-prone. By wrapping that logic into a function, you make your code easier to read, easier to modify, and much easier to reason about.
Functions matter because they change how we think about programs. Instead of seeing code as a long chain of instructions, you start to see it as a set of well-defined building blocks. Each block has a responsibility, and that makes complex systems manageable.
When you don't organize logic this way, problems tend to pile up. Small changes require touching many places, mistakes are harder to isolate, and understanding what the code is doing becomes exhausting. Functions are the tool that breaks this cycle.
Here we see the basic structure of a function in Python. Defining a function means describing a behavior and giving it a name, but nothing actually happens yet. This separation between definition and execution is fundamental. It lets you decide when and how often that behavior should run.
In the example, the first part creates a function called greet and specifies what it should do when it runs. Notice that simply defining it produces no output. The action only happens later when the function is explicitly called, and that's when the message is printed.
Parameters are what make functions truly useful. Instead of hard-coding values inside a function, you leave placeholders that will be filled when the function is called. This allows the same logic to adapt to different situations without being rewritten.
In this example, the function no longer prints a fixed message. It accepts a name from the outside and uses it when it runs. Calling the function with a specific value produces a personalized result, showing how one definition can handle many different inputs.
So far, functions were doing something visible, like printing, but return values change the role of a function completely. A function can compute a result and hand it back to the rest of the program, which means its output can be stored, combined, or reused elsewhere.
In this example, the function performs a calculation and gives the result back instead of displaying it directly. That return value can then be assigned to a variable and used later, showing how functions become part of larger expressions rather than just isolated actions.
This distinction is crucial. Printing a value is about visibility. Returning a value is about computation. When a function returns something, it becomes part of the program's logic and can be combined, stored, or passed forward. That's what makes functions useful in real programs.
Looking at the two functions, they may seem similar, but they behave very differently. The first one only displays a result and then it's gone. The second one actually produces a value that the rest of the code can work with. That's why, outside of quick checks or debugging, returning is almost always the better choice.
Functions are not limited to a single input. Very often, a behavior depends on several pieces of information at the same time. By accepting multiple parameters, a function can combine values, relate them, and express more meaningful operations in a compact and readable way.
In the example, the function receives two values and uses them together inside its body. What matters here is how arguments are matched to parameters. Values are assigned in order from left to right. That's why the position of each argument is important unless you explicitly say otherwise.
Default parameters add another layer of flexibility to functions. They let you define a sensible behavior even when no input is provided, so the function remains usable without forcing the caller to specify every detail.
In this case, the function already knows what to do if no name is passed in. When a value is provided, that default is simply replaced. This makes the function easier to call in common situations, while still allowing customization when needed.
Variable scope defines where a name exists and where it can be used. When a variable is created inside a function, it belongs to that function only. This boundary is intentional. It keeps different parts of a program from interfering with each other.
In the example, the variable is created and used successfully inside the function, but once execution leaves that function, the name no longer exists. Trying to use it afterward causes an error. This behavior protects your code from accidental side effects and is one reason global variables are usually avoided.
Docstrings are about intent and communication. They explain what a function is meant to do, not how it does it. This makes code easier to understand for others and for your future self when you come back to it later.
Here, the description lives right inside the function using a standard format. That short explanation doesn't affect execution, but it adds clarity and structure. Tools and editors can also read it automatically, turning your code into something that documents itself.
This is where functions stop being a programming detail and become a way of thinking. In data analysis, almost every step can be expressed as a function, something that takes data in, applies a rule, and produces a result you can build on.
The example shows a simple statistical operation wrapped into a function. Even though it looks basic, the same structure applies when working with larger data, multiple variables, or entire datasets. Once the logic is isolated, it scales naturally from small values to real analytical workflows.
At this point, functions are not just a language feature, but a design tool. Good functions communicate intent, avoid repetition, and stay focused on a single task. These practices are what separate code that merely works from code that can be understood, reused, and trusted.
All these guidelines aim at the same goal: clarity. Clear names tell you what a function does without opening it, fewer parameters reduce cognitive load, and modular functions are easier to test and adjust. When everything is small and focused, the whole program becomes easier to reason about.
At this point, you've completed a full pass through control flow. You've seen how decisions, repetition, and structure allow a program to move beyond linear execution and respond to different situations in a controlled way.
This slide marks the end of the lesson and closes the loop on everything shown so far. You now have the tools to write code that branches, repeats, and adapts. The next lesson is simply announced here, as a transition to what comes after.